2 or 3 washers on here and it wasn't accelerating. What does that tell you about, are these forces in balance?
When it's not moving?
Yeah.
Mm-hmm.
I mean, that's a simple question. Yeah, okay. But once, let's say now you put 10 washers on there. What's going to happen? So let's talk about the motion now. So let's say you put 10 or 15 or whatever, however many you need to put on there. You put 20 on. What happens now?
The weight overcomes the force of the string.
It overcomes the static friction.
It overcomes the static friction. How would you describe the motion of the cart? I'm just asking for a very simple word. Goes forward. Is it moving forward?
Accelerates.
It accelerates. Okay, so we're accelerating. Okay, now we're accelerating.
Once you've gotten rid of that static friction, then it becomes much less of a factor, so the thing will pick up speed. Because now you're just dealing with
Something that we call it. There's still friction there. There's still friction there. There's still friction there. But I think you're actually right. That what we call dynamic or kinetic friction is probably a little less. But once the point is that it only rises to a certain level and then you overcome it. Okay, so we're accelerating. What does that tell us about the balance of forces in this situation? This object, what does it tell us about the balance of forces here?
The force of the string is greater than the force of static friction.
And what does it tell us here?
Force of the weight is greater than the force of the string.
Yep. Okay. Now, one of the things we talked about that's getting into maybe a little bit more detail than we need to get into is oftentimes in these kind of physics problems, we ignore the string as a mass. What did you all find? Was that do you suspect that was a reasonable assumption?
Okay, that question.
Well, you all what did you find the string's mass was?
2
2 grams?
Yeah.
And how much is a one washer?
I found it's the same.
About 1 gram?
Yeah, we found it was the same as the small washer. But we
The
also
string?
weighed in terms of ounces, but the weight of the string changes depending on how much of it is hanging over the edge of the table at any given time. In terms of the bottom system.
Okay, that's interesting you're saying that, though, because let's think about this. So are you saying that the string doesn't matter in the horizontal part?
no. You have less friction on top because there's less string too.
That's what you said.
I mean,
But what else matters about that?
could you say that again? Could you ask the question again? The mass of you're asking if the mass of the string matters, the weight of the string matters in
Maybe
terms
I'm
of the
getting too much
horizontal.
detail. There's a portion of the string that's horizontal and there's a portion of the string that's vertical. And what you're pointing out is that part of the string adds, the vertical part's important. Why?
Because it's for gravity.
It's adding to the weight.
Mm-hmm.
But
It also has less friction because as long as that string is on top of the table, there's a frictional force involved too. So yes, it becomes more of a weight on the end.
you're talking about the
And
string
there's
rubbing.
less friction on the top.
You're talking about the string rubbing against this table. Yeah. Okay.
But then there's more, once more string hangs over the edge, then,
It's both of them.
right. Because if it's like this, equal parts of string are on top of the table and on the bottom of the table, then only 25 thousandths of the string is really affecting the weight in the vertical system. But as more string falls, then more weight, in a sense, is added. That's it.
And there's less drag on the
Yeah.
surface because there's less
Ours only
length.
touched on the edge of the table, though.
Yeah, we
Didn't
had our
touch-
car
Yeah,
the
it-
other way.
Stop. It only really brushed up here.
Yeah, our car.
We didn't
When the
have-
car is really close to it, when the car is really close to the edge, but the further the car is, there's more of it's going to be laying on
Our
top of the
support
table.
braces.
It's not much. We're not talking much
Yeah,
here.
yeah.
Our support braces
Ours
are
were
on top.
higher, so it really
It really
didn't.
touched the
I
land.
think it's-
So I
yeah.
want to ask about the test you all did. So you tested the friction of the tires with and without the tires.
Yes.
So can you describe to everybody what the experiment you did? So when you were asking me a question about when you pulled it, what did you find when you pulled all the rubber tires off?
Okay, when we started with pulling the tires off the smaller wheels, and the speed increased, and then we removed both the large and the small, and it really increased. And the question I asked you was, what did mass have to do with it? And you asked us to test that.
Well, let's hold on. So what?
Okay.
So what did that? So you had two. So we came up with two. You mainly came up with a hypothesis as to why it was going faster when you pulled the tires off.
Yes, was it
accelerating more?
Was it just the lack of friction, because we had less friction with the plastic wheel? Did the mass of the tires have anything to do with the fact that,
Yeah.
there we go.
But you can take the tires and put them on top of the car and see if that made a difference.
That's what we did, we just didn't
Good
finish
idea.
testing. Yeah.
So does everybody understand that? Great, a great experiment, right? So
Michael Marion.
So they're trying to figure out it could be both, it could be one or both of two different effects, friction or mass. So they just piled the tires on top, so the mass is the same. What'd you find?
You didn't finish, you were missing too much up there.
Okay, yeah, okay. Well, great. So we have results to be continued. We have to finish that one. So that's a great experiment. Okay, so then you started putting more. So you put more and more mass on the. So what did we find as you doubled and tripled and quadrupled the mass? What did you find, generally speaking? Okay. And did it increase in a way that you made? What would you expect if you double the mass? What did you expect to happen to the time? Okay, now I'm gonna have to be careful here because I don't want to get into. So why? I mean, I understand that sounds pretty good. Double the mass half the time.
That's what we found happen.
What do you know is gonna happen about the motion when you double, or what do you, let's know, but what, in terms of Newton's laws, what's gonna happen when you double the mass? In terms of Newton's laws, what about the motion? What's gonna increase? Force equals F equals ma. So if you're doubling the force, you're doubling the acceleration. Okay?
Your mass doesn't change in if that's the case.
Right. If your mass doesn't. So if you double the force, your acceleration doubles. Okay? If you triple the force, your acceleration should triple. Now, how does that relate to time? That's a little more complicated. And here's why it's more complicated. What is acceleration? Let's talk a little bit about what is acceleration. What's acceleration mean? If your acceleration doubles, what does that mean exactly?
Could you do just distance over time?
Okay, there we go.
Because we did, and we found out the actual speed, not speed, but velocity, I suppose, would be more concerned.
Well, can you do distance over time?
That's what I meant, I don't know.
So what's distance over time?
It's going to give us
Speed.
speed.
Yeah,
Not
just, right.
Okay, it's speed. I mean, it's the magnitude of the velocity.
Mm-hmm.
Okay, so the velocity, the speed equals what?
We did V over T.
Now, when is this equation okay to use?
straight line.
When it's only one going in one direction.
Well, you're going in one direction here. I mean, so,
Yeah, it is average, because it's not from start to, yeah, because it can.
I like it. What did you guys say over there?
It's an average
It's
speed.
an average speed. I'm gonna call it velocity. I'm gonna call it velocity.
Yeah,
That's what
well.
I call it. So you have an average, so you all figured out the average velocity in every case?
Mm-hmm.
Great. But is the velocity constant in your? Okay, so you're going, so here's one of the things that we have to, this is where you want to use what you know about these simple concepts about motion. If you're accelerating if you have a constant acceleration, what does that tell you about your velocity?
It's increasing.
It's increasing in a very special way, very simple way.
Constantly.
It's a
Yeah.
constant increase. Linear.
Right?
So or is it?
It is.
Yeah, I mean, it's
As one increases, so
increasing
does
at a
the-
constant rate. It's increasing at a constant rate. So you're
Same
going,
slope.
where are you starting?
Zero.
Your velocity at the beginning is what? Your speed, zero. Okay? I mean, I'll just draw it real quick. Time equals zero. You have zero velocity, and you end with some velocity. And what I'm telling you is that if you have a constant force,
Straight line.
it just increases, your velocity is increasing the same amount every second.
And it becomes a quadratic.
You grab time versus,
Distance.
what was that?
No, this is velocity.
Yeah, that was time versus time. Because
Velocity
our graph wasn't
with velocity and time?
linear. I know, with,
No, time and weight.
time, yeah.
Okay, it's a completely different graph. And it shouldn't be linear,
Yeah.
okay?